It takes only 8 minutes for light to travel from the sun to the Earth. But if the cosmos decided to turn off our sky, we wouldn't even know it had begun until it was already over. We live under a quiet blue dome, unaware of the violent physics playing out just beyond our atmosphere. This is the story of the absolute boundaries of survival and why we are currently living on borrowed time. When we look up at night, we see the glowing lights of our cities, tiny sparks of human civilization standing against the infinite, freezing abysm of space. We feel safe. We feel permanent. But here's what makes this truly mind-bending. The shielding that keeps us alive is so thin that a minor shift in cosmic activity could strip it away in a heartbeat. When we think about extinction, we usually imagine a slow, creeping shadow. We picture dinosaurs starving over decades, or ice ages freezing continents over thousands of years. But physics doesn't operate on human timelines. In the deep expanse of space, events occur that can rewrite the chemistry of a planet in a fraction of a second. If one of these cosmic hammers strikes, our atmosphere changes instantly and the surface of our world turns into a thermal chamber. This introduces a critical physical concept known as the 2-hour horizon. It is the absolute point of no return for planetary life. Within this 2-hour window, the energy transfer determines whether a planet remains a living world or becomes a sterile rock. If the thermal load delivered to the atmosphere exceeds a critical threshold, the oceans begin to boil and heat penetrates the ground. This is where the physics gets strange. The moment the radiation hits, the atmosphere acts like a thermal blanket, trapping the heat and driving it downward. If the energy dump continues, the surface rock itself begins to absorb the thermal surge. Once that heat penetrates past a critical depth, the feedback loop becomes irreversible. The oceans turn to steam and the entire surface becomes a molten wasteland. Every second counts. If the planetary shields can withstand the initial 2 hours of intense radiation, the deep rocks will remain cool. But the real mystery lies in how a planet determines this survival threshold. It is not just about the size of the shield. It is about the rate of energy dissipation. If the energy enters faster than the atmosphere can radiate it back into space, the system collapses. To understand this survival threshold, we must first look at what we get wrong about the biosphere. We believed that the surface was the only home for life. We looked at forests, grasslands, and shallow oceans and saw the entire sum of biology. But this is a fragile illusion. The surface is vulnerable, a thin skin exposed to the unpredictable currents of space. If a cosmic blast wipes out the forests, we assume that life is finished. However, the true motor of Earth's biology is hidden deep beneath our feet, locked inside the dark pressure of the Earth's crust. This is the Deep Biosphere, a massive network of microbes that exist miles below the soil. They don't need the sun. They don't care about photosynthesis or the sky. They feed on hydrogen, sulfur, and the raw chemical energy leaking from the core. This subterranean engine of life is completely immune to stellar shocks. A study in Nature Geoscience estimated that this deep biosphere holds up to 19 billion tons of carbon, hundreds of times the mass of all humans. This means that most of the disasters we read about are not true extinctions. They are merely superficial adjustments. An ice age is just a cold snap. A supervolcano is a brief dust storm. Even if surface temperatures drop by 50 degrees, the deep crust remains warm and stable. The microbes down there continue their slow, chemical lives, unaffected by the chaos above. For them, a nuclear winter is nothing more than a quiet afternoon. To truly kill a planet, you must break the shielding of the crust itself. But here's the shocking truth. To destroy this deep engine, you must deliver enough energy to boil the oceans and cook the rock down to a depth of several miles. If a cosmic blast doesn't dump enough heat to penetrate the deep rocks within those first 2 hours, the deep biosphere will survive. The surface will be sterilized, the forests will burn, the oceans will boil. But the deep roots of life will remain intact. When the sky clears millions of years later, these subterranean survivors will emerge to recolonize the ruins. How much energy does it take to cross this ultimate boundary? We see scarred planets that crossed their own horizons long ago. Mars lost its atmosphere as its core cooled. Venus suffered a runaway greenhouse effect that boiled its seas. Earth, however, has held its shield for 4 billion years. We live in a protected bubble, shielded by a thick atmosphere, a magnetic field, and oceans acting as heat sinks. Yet, this protection has a limit. There are forces in the universe that can pierce these shields like a bullet through paper. The cosmos is a violent furnace where stars explode and black holes collide. We think of asteroids as the ultimate destroyers, the rocks that wiped out the dinosaurs. We look at the Chicxulub impact as the peak of destruction. But when we apply the strict physics of the 2-hour horizon to that legendary collision, the math reveals a startling mystery. The impact was violent enough to kill the surface giants, but it failed to cross the threshold of total sterilization. The energy calculations show that the planet was spared from the ultimate heat death by a surprisingly thin margin. If the asteroid had been just slightly larger, or moving just a bit faster, the heat would have boiled the oceans dry. This raises a dark question. How close did the Chicxulub impact actually come to breaking them? 2-hour barrier. And what physical shield saved the Deep Biosphere from being cooked alive in the dark? To find the answer, we must examine the physics of the impact itself, tracking the energy as it collided with the Earth's armor. It is a journey that takes us to the dark caverns beneath the Yucatan Peninsula, where the rules of survival were rewritten in a single hour. 66 million years ago, a mountain of rock the size of Manhattan was screaming toward Earth. It was 10 kilometers wide, moving at 45,000 miles per hour, roughly 70 times faster than a commercial jetliner. When this colossal projectile slammed into the shallow waters of the Yucatan Peninsula, it exploded with the fury of 100 teratons of TNT. That is equivalent to billions of Hiroshima-sized atomic bombs detonating at the exact same moment. The impact carved a crater 150 kilometers wide and 30 kilometers deep. In a fraction of a second, the energy of the collision vaporized cubic miles of ocean water and bedrock, launching a massive column of debris high into the upper atmosphere. The world as the dinosaurs knew it was erased in a single heartbeat. But the real mystery lies in how the atmosphere responded to this kinetic energy. As the vaporized rock climbed, it expanded into the vacuum of space, forming an incandescent plume of superheated vapor that looked like a glowing, golden veil draped over the planet. As this plume cooled, it condensed into trillions of tiny glass droplets called spherules. Falling back to Earth, they friction heated the upper atmosphere, turning the sky into a radiating heater. This intense infrared pulse cooked the surface, igniting global wildfires. But here's what makes this truly mind-bending. The sky at night did not go dark. Instead, it glowed with a constant brilliance as the re-entering glass droplets shone like a torrential rain of hot red shooting stars. This global firestorm was followed by a decade-long impact winter. Billions of tons of sulfur, soot, and dust floated into the stratosphere, forming a toxic shroud that blocked the sun. Without sunlight, photosynthesis stopped and the food chain collapsed, wiping out 75% of all species. The surface of our planet was a freezing, sterile wasteland. Yet despite this violence, the spark of life was not put out. This is where the physics gets strange. The energy of the impact, though large enough to reshape the surface, was not enough to penetrate the deeper layers of our planet. The surface was fragile, but the subterranean engine was resilient. To understand this, we have to look at the numbers. The physics of planetary sterilization require an energy input that dwarfs Chicxulub. To boil the oceans and cook the entire surface, you need to deliver roughly 10 to the power of 26 joules of energy. The Chicxulub impact delivered only a tiny fraction of that number. It was like dropping a single hot coal into a freezing swimming pool. The thermal energy was concentrated at the surface, and while it destroyed the forests and the giants, it could not penetrate the deep armor of the Earth. The physical laws of thermodynamics dictate that rock is an incredibly poor conductor of heat. When the thermal pulse roasted the surface, the intense heat did not travel deep. It only warmed the top few inches of the crust in the first critical hours. Underneath the charred soil, miles below the burning forests, the temperature of the solid rock did not rise by even a fraction of a degree. This deep crust acted as a massive thermal shield, absorbing the energy and dissipating it over thousands of years. The subterranean biosphere, the network of simple life forms residing in the deep rocks, did not experience the impact winter. They did not feel the heat pulse. For these deep-dwelling organisms, the extinction of the dinosaurs was a non-event. They were sealed in their geological vaults, isolated from the sun and the atmosphere, continuing their metabolic cycles as if nothing had happened. They represent the invisible engine of the planet, the core mass of biology that keeps Earth alive during its darkest times. But the crust was not the only shield. A similar shield protected the deep oceans. Water has a high specific heat capacity, meaning it takes a massive amount of energy to raise its temperature. While the top layers of the sea were acidified and choked with soot, the deep ocean plains remained cold, dark, and stable. The abyssal plains and hydrothermal vents were insulated from the thermal chaos at the surface. The organisms living in these deep-sea environments did not rely on sun-driven food chains. They fed on chemical compounds venting from the Earth's interior. They survived the 10-year darkness because they were already living in a world of perpetual night. The planetary shields held Chicxulub was a local shock to the system, but not a fatal blow to the biosphere. The deep roots of life remained intact. This reveals a fundamental truth. Survival is a function of depth. The deeper you go, the more stable the environment becomes, and the harder it is for any surface catastrophe to reach you. An asteroid impact is a violent, dramatic event, but its energy is spent mostly in the atmosphere and on the thin outer skin of the planet. It lacks the raw physical power to cook the deep crust or boil the oceans down to their beds. To achieve true sterilization, a cosmic threat must deliver its energy in a way that bypasses these local thermal shields. It must attack the planet with a different kind of weapon, one that does not rely on a single physical collision. And this is where the cosmos becomes truly terrifying. This brings us back to the 2-hour horizon. If a physical impact cannot boil the oceans or cook the deep rocks within 2 hours, then what can? The universe has other, more subtle methods of destruction. What if the threat does not come from a solid rock, but from a silent beam of invisible radiation crossing light years of empty space? What if the sky itself becomes a silent killer, stripping away the atmosphere without warning? As astronomers scan the deep cosmos, they have found sources of energy so intense that they make an asteroid impact look like a firecracker. And one of these silent sweeps might have targeted our world in the ancient past, threatening the planet in a way no asteroid ever could. But did it cross the boundary of the deep shields? The cosmos doesn't always advertise its threats. While an asteroid collision is preceded by a rock tracking across the night sky, the most powerful explosions in the universe arrive without warning, traveling at the speed of light. By the time we detect them, the damage is already done. These are gamma-ray bursts, or GRBs. They are the death screams of massive stars collapsing into black holes, or the violent mergers of binary neutron stars. When these stars collide, they focus their energy into narrow, hyper-concentrated jets of gamma radiation. A single massive GRB can release more energy in 10 seconds than our sun will produce in its entire 10 billion-year lifetime. If one of these violent beams is aimed directly at Earth from across the galaxy, there is no shield in our solar system that can stop it. It is a silent, invisible executioner. But here's what makes this truly mind-bending. The real danger is not the direct heat of the beam, but the chemical cascade it triggers in our sky. Imagine a GRB detonating 6,000 light-years away. To our telescopes, it appears as a brief flash on the edge of the Milky Way. But for our atmosphere, it is a chemical sledgehammer. The initial wave of gamma rays strikes the upper atmosphere, colliding with nitrogen and oxygen molecules. The extreme energy of the radiation tears these stable molecules apart, forcing them to recombine. This reaction produces nitrogen oxides, specifically nitrogen dioxide. This is a heavy brown gas that is highly toxic to living tissue. Within minutes, the upper sky turns a dark, muddy brown, forming a global shroud that blocks out the sun. This is where the physics gets strange. The nitrogen oxides immediately begin to destroy the ozone layer, dismantling the chemical bonds of the ozonosphere like an invisible molecular web evaporating under a solar torch. Within days, 99% of the Earth's ozone is erased. Without this vital shield, the planet is exposed to the raw ultraviolet radiation of the sun. The atmosphere is no longer a protective blanket. It is a magnifying glass focusing a solar torch. When the sun rises, the ultraviolet rays burn the surface with unprecedented violence, striking the cells of every plant and animal exposed to the open sky. The UV rays create pyrimidine dimers in the DNA, forcing adjacent thymine bases to bond incorrectly. This molecular distortion breaks the replication process of cells, causing massive mutations, cell death, and rapid decay. At the same time, the sky's chemistry changes the water cycle. The nitrogen oxides in the air react with water vapor, creating nitric acid. The clouds no longer release clean water, they rain diluted acid. This acid rain falls across the continents and oceans, poisoning soils, killing vegetation, and disrupting the chemistry of shallow seas. The surface becomes a toxic, acidic furnace under a brown sky, with cells burning under UV light and roots dissolving in acid. But how does this crisis measure up against the 2-hour horizon? If we apply the 2-hour clock to this radiation sweep, the speed of destruction is terrifying. Within the first 2 hours, the surface of the planet is sterilized. Any organism exposed to the sky is dead or dying. But the real mystery lies in how the planet's deep layers respond. Yet, once again, the physical laws of nature build an unexpected barrier. The radiation sweep is incredibly effective at killing the surface, but it cannot penetrate the depths. Liquid water is a highly effective absorber of ultraviolet rays. The top 3 feet of the ocean are saturated with lethal UV, but the water below absorbs the energy, leaving deeper layers safe. Marine life living just 10 yards down doesn't feel the burn. While the toxic brown clouds alter the chemistry of shallow seas, the deep ocean remains chemically stable. The deep-sea ecosystems, insulated by miles of water, continue their lives without interruption. They feed on chemical compounds venting from the Earth's interior, completely unaware of the chemical collapse occurring in the sky above. For them, the destruction of the ozone layer is a distant whisper. An even stronger shield exists within the solid crust of the Earth. The gamma rays themselves cannot penetrate more than a few inches of rock. However, the collision creates a shower of secondary particles, muons and pions. These particles penetrate deep into the crust, delivering an ionizing radiation dose. For shallow underground life, this is a threat. But as we go deeper, rock density wins the physical battle. At a depth of half a mile, rock acts as a perfect shield, stopping even the most energetic muons. The deep subterranean biosphere, located miles beneath the continents, remains completely untouched. This underground engine of life, powered by radioactive decay and geothermal heat, is completely isolated from the sun and the atmosphere. It continues to run, silent and resilient, immune to the cosmic storm raging above. This means the GRB sweep, like the Chicxulub impact, fails the test of total sterilization. The 2-hour horizon is crossed for surface life, ending surface ecosystems in minutes, but deep reserves remain secure. Microbes in the deep rocks and creatures of the abyss are completely insulated. They don't know the ozone layer is gone, nor do they care about the brown sky or acid rain. The planetary engine survives because its core biosphere is buried too deep for the cosmos to reach. The physical barriers of water and rock are simply too thick for the radiation to pierce. The surface is fragile, but the heart of the planet is resilient. But this leaves us with a deeper, more unsettling question. If an impact cannot boil the oceans, and cosmic radiation cannot reach deep rocks, is Earth truly invulnerable? Is there any force in the universe that can deliver enough energy to cross the 2-hour horizon for the entire planet? To find the answer, we must look closer to home. We must look at the sun. The sun is our life giver, but it is also a sleeping giant. If its physics changes, our shields of rock and water won't save us. What solar event could turn our protector into a planetary furnace? And how does the physics of a dying star rewrite the rules of survival? It is a journey that takes us from distant stars to our own companion. When we think of cosmic danger, we usually look for giant rocks or visible stellar explosions. But the cosmos has a terrifying way of weaponizing invisible fundamental forces, altering the fabric of reality itself. Consider the magnetar. Born from the crushed core of a collapsed stellar giant, a magnetar packs the mass of a star into a sphere the size of a small city, spinning hundreds of times per second. But its most extreme property is its magnetic field, reaching an intensity of 10 to the 11 Tesla. This number is hard to comprehend. To put it in perspective, 10 to the 11 Tesla is 100 billion Tesla, a force trillions of times stronger than the magnetic field protecting the Earth. If a magnetar were moved to the distance of the moon, its magnetic pull would rewrite the laws of chemistry. This is where the physics gets strange. At these extreme levels of magnetic force, the behavior of matter becomes unrecognizable. The magnetar itself glows in brilliant X-rays in the pitch-black interstellar darkness, surrounded by an invisible, twisting web of magnetic lines. If ordinary matter enters this field, the electron clouds around every atom are violently compressed. The electrons are stretched into long, thin, needle-like filaments, transforming the atoms of matter into submicroscopic needles. Because chemical bonds cannot hold under this distortion, organic molecules instantly dissolve. If you stood near a magnetar, your physical structure would disintegrate as your atoms stretch into. Microscopic threads dissolve in your body into a cloud of ionized gas. But the real mystery lies in how these distant stars can strike our planet across the void of space. Magnetars are under immense internal stress, their super-dense iron crusts constantly cracking under the pressure of magnetic lines, causing massive ruptures called starquakes. In 2004, a starquake on a magnetar 50,000 light-years away released enough energy in a fraction of a second to saturate space satellites and ionize our upper atmosphere. But here's what makes this truly mind-bending. An event so distant that its light took 50,000 years to reach us physically altered our planet's atmosphere in a millisecond. If a starquake occurred closer, say within 10 light-years of our solar system, the initial shockwave of X-rays and gamma rays would hit us like a cosmic fist. Within seconds, this high-energy wave would slam into our magnetosphere, compressing our magnetic shield and shoving it down into the upper atmosphere. The air molecules would absorb this energy, causing massive ionization. The ozone layer would be stripped away, leaving our surface exposed to the raw radiation of the sun. A brilliant ultraviolet aurora would paint the sky in glowing, unnatural colors, a lethal light show covering the entire globe while the ground is bombarded by high-energy particles. While a magnetar starquake is a brief, intense pulse, other cosmic explosions offer a slower, more grinding destruction. A supernova occurring within 30 light-years of Earth represents a slower, decades-long radiation bath. The collapsing star detonates, ejecting outer layers into space and generating a continuous bombardment of relativistic cosmic rays, which are protons and atomic nuclei accelerated to near the speed of light. This relentless radioactive wind destroys the ozone layer, triggering ecological collapse. The constant ionization changes air chemistry, generating nitrogen oxides that precipitate as nitric acid, while secondary radiation showers the surface with pions and muons, damaging the reproductive systems of land organisms over generations. Now let us apply our 2-hour horizon to these radiation scenarios. Within 2 hours, the surface of the Earth becomes a hostile zone as the ozone layer is depleted. Plants and animals on land are exposed to intense ultraviolet rays that break down DNA structures, leading to rapid cellular death. The surface food webs break, but the physical structure of the planet remains intact. This highlights the profound contrast between the fragility of our surface and the deep resilience of the planetary system. While the surface of our planet is vulnerable, the base of life is not. Radiation has a fundamental weakness. It is easily absorbed by mass. A layer of water just a few meters deep is an effective shield against ionizing radiation. The deep ocean is insulated from the cosmic storm. The dark abyssal plains and hydrothermal vents continue to operate, powered by geothermal heat completely decoupled from the atmosphere. But the real secret to our planet's survival lies even deeper, beneath the seabed. The solid rock of the continental and oceanic crust acts as a dense physical barrier, absorbing the radiation before it can reach the interior. The vast community of microscopic life residing in the deep rock pores, known as the Deep Biosphere, remains completely immune to the cosmic storm. These simple organisms do not rely on sunlight or surface oxygen. They sustain themselves on chemical reactions, using hydrogen and sulfur derived from the rock. The subterranean crust acts as the invisible motor of the Earth, keeping the engines of biochemistry running in the dark. Over centuries, the atmosphere would recover, the ozone layer would reform, and the deep life would eventually migrate back to the surface. But what if the threat is not an external cosmic wave, but a chemical poison bubbling up from the very engine that keeps our planet alive? To understand the true limits of survival, we must look inward, at the massive volcanic engines that have rewritten our history before. While the cosmos offers spectacular ways to threaten the biosphere, the Earth itself possesses internal engines of immense destructive power. We do not need to look to the stars to find events that rewrite geological history. The most devastating extinctions in our planet's past were not caused by cosmic impacts, but by massive volcanic eruptions known as flood basalt events. The prime example of this internal fury occurred 252 million years ago, during the Permian extinction, with the creation of the Siberian Traps. This was not a typical volcanic eruption with a single mountain blowing its top. Instead, Massive fissures in the crust ripped open across millions of square miles, venting molten rock for hundreds of thousands of years. This is where the physics gets strange. The sheer volume of erupted basalt was enough to bury the entire United States under a mile of solid rock. These eruptions created massive lakes of liquid fire, glowing in deep red and gold, flooding whole continents and venting billions of tons of gases under a sky darkened by ash. But the liquid rock itself was not the real killer. The true devastation came from the greenhouse gases trapped within the crust that were suddenly released. These eruptions released massive volumes of carbon dioxide and sulfur dioxide, triggering a runaway greenhouse effect. Global temperatures spiked, and the oceans warmed rapidly, losing their ability to hold dissolved oxygen. But the real mystery lies in how this temperature spike initiated a toxic cascade in the global oceans. As the waters became warm and depleted of oxygen, a condition known as anoxia, the marine food webs collapsed. The lack of oxygen created a perfect breeding ground for anaerobic green sulfur bacteria. These organisms thrive in stagnant, oxygen-poor waters, using sulfur compounds for energy. As they multiplied, they produced vast quantities of hydrogen sulfide gas, turning ocean basins into stagnant pools. Under a bruised sky, ocean waters began glowing in an eerie, anoxic purple, venting toxic gas into the atmosphere. This gas acted as a metabolic poison, stopping cellular respiration in land animals, while chemically destroying the ozone layer and exposing the surface to solar ultraviolet radiation. This cascade resulted in the Great Dying, the most severe mass extinction in Earth's history, where 96% of marine species and 70% of terrestrial vertebrates disappeared. But here's what makes this truly mind-bending. This extinction did not occur overnight. It unfolded slowly over hundreds of thousands of years. This gradual pace is critical when we analyze the physics of survival. Because the disruption was slow, the planet had time to develop thermal refuges. Organisms could slowly migrate, adapting to cooler latitudes or deep water zones that remained insulated from the worst of the toxic plume. The continuity of life was maintained because the chemical transitions did not cross the critical threshold of absolute sterilization. This highlights the profound contrast between the fragility of our surface ecosystems and the resilience of the planetary crust. The surface of our planet is vulnerable, easily poisoned by chemical shifts. But the base of life is not. The deep microbial biosphere, living in the rock pores miles beneath the continents, remained completely insulated. The crust acts as the invisible motor of the Earth, keeping life alive even when the oceans turn to poison. Now let us contrast these deep geological events with the modern threats that dominate human anxiety, like nuclear war or severe geomagnetic storms. A full-scale nuclear conflict would detonate thousands of warheads, throwing soot into the stratosphere. This would block 90% of incoming sunlight, creating a global nuclear winter that freezes agricultural heartlands and causes mass starvation. Alternatively, a severe geomagnetic storm, caused by a massive solar eruption, could induce massive electrical currents in our power lines. Within minutes, transformers would burn, shutting down the global electrical grid and communication systems. A solar superstorm like the Carrington event of 1859 would leave entire continents dark and without power for months. If we apply our 2-hour horizon here, the transition is immediate. Within 2 hours of a solar superstorm or nuclear strike, human civilization collapses as power grids fail and networks go silent. The systems keeping 8 billion people alive are incredibly fragile. But from the perspective of planetary physics, these events are minor fluctuations. A decade of nuclear winter is a blink of an eye in geological time. The atmosphere slowly clears, the sun returns, and ecosystems recover. The microscopic life deep in abyssal sediments do not register the event, continuing their chemical metabolism unaffected by the surface freeze. Thus, the internal forces of the Earth and the vulnerabilities of our modern civilization fail to cross the barrier of absolute sterilization. They can erase human history and reshape the surface biosphere, but the deep rock and ocean systems remain insulated, preserving the molecular code of life. But what happens if the incoming threat is so massive that no geological shield can absorb it? What if the hammer is not a distant radiation wave or a slow volcanic leak, but a kinetic impact of such magnitude that it treats the entire planet as a thermal target? To find the boundary of absolute sterilization, we must look at the giants of the solar system, and examine what happens when a 500-kilometer monster collides with our world. When we search for the boundary of absolute sterilization, we must look beyond volcanic eruptions and radiation storms. We must find an event that injects enough energy into the planetary system to break the physical shields of water and rock. This boundary is crossed when we consider the collision of a giant asteroid. We are not talking about the 10-kilometer rock that wiped out the dinosaurs. That was a minor impact. We are talking about a monster, an asteroid 500 kilometers in diameter, roughly the size of the dwarf planet Ceres. There are objects of this size orbiting in the asteroid belt, and in the early history of the solar system, such collisions were a regular occurrence. An impact of this scale releases a kinetic energy of 10 to the 26 joules. That is equivalent to billions of Hiroshima-sized nuclear bombs detonating at the same instant. It is a blow that treats the Earth not as a planet, but as a thermodynamic target, shifting its energy balance permanently in a fraction of an hour. To put this in perspective, a 500-kilometer object has 125,000 times the mass of the dinosaur-killing asteroid, carrying enough kinetic energy to melt the entire crust. This is where the physics gets strange. When the asteroid strikes the surface at 20 miles per second, the crust of the Earth is pushed aside like thin paper. The impactor does not simply dig a crater, it punches through the lithosphere, compressing the mantle and generating a shockwave that travels through the entire body of the planet. Millions of tons of crust and mantle are instantly vaporized, reaching temperatures of several thousand degrees. The solid crust behaves like a fluid, disintegrating and moving outward in giant ripples, like waves in a lake of stone. This gas of vaporized rock is ejected into space, escaping the gravity of the Earth before falling back under its pull. But here's what makes this truly mind-bending. As the vaporized rock re-enters the atmosphere, it condenses into microscopic droplets, releasing its thermal energy into the air. Within minutes, the atmosphere is wrapped in a sea of rock vapor, glowing in an incandescent orange. The sky turns into a high-pressure infrared broiler, radiating heat downward onto the surface with intense power. The atmosphere becomes a thermal oven, and the heat flux at the surface reaches levels that instantly ignite forests and melt exposed rocks. Now let us apply our 2-hour horizon to this kinetic nightmare. If an impact of this magnitude occurs, the transition is immediate and absolute. Within 2 hours, the thermodynamic balance of the surface is shattered. The temperature of the atmosphere rises to hundreds of degrees, and the oceans begin to boil. The water does not evaporate slowly over centuries. It boils at a rate of several centimeters per minute, venting massive plumes of high-pressure steam into the sky. But the real mystery lies in how these massive oceans evaporate, transforming into white, desolated salt canyons under a blood-red sky. Within a short period, the entire volume of the oceans is converted into a thick, choking envelope of steam. The dark, cold trenches of the deep ocean, which survived magnetar quakes and volcanic eruptions, are exposed to the heat. The water column is heated to the boiling point from the surface down to the seafloor, destroying the hydrothermal vent communities. The proteins that form the basis of cellular life break down, sterilizing the abyssal plains. But the sterilization does not stop at the empty ocean floor. The thermal energy of the atmosphere and the boiling steam continues to interact with the planet. Over the following weeks and months, the heat from the surface is conducted downward into the solid crust. The rock is a slow conductor of heat, but the thermal gradient is steep. The heat wave slowly penetrates the continental and oceanic crust, raising the temperature of the rock pores. Once the temperature passes 120 degrees Celsius, the biochemical limit for cellular life is exceeded. This is where we see the ultimate contrast between surface vulnerability and the limits of subterranean resilience. In previous planetary crises, the Deep Biosphere, which exists in the microscopic pores of solid basalt miles underground, acted as the invisible motor of the Earth. It was the reservoir of life, completely immune to the surface chaos. But a 500-kilometer impact is different. The creeping thermal wave slowly cooks the subterranean crust week after week, baking the rock until every living cell is reduced to carbon ash. The crust becomes a sterile zone of heated rock, completely devoid of genetic material. The resilience of life is finally overridden by the laws of thermodynamics. The Earth is converted into a sterile rock, wrapped in a dense shroud of steam and carbon dioxide, spinning silently in the dark. It would take millions of years for the surface to cool, for the steam to condense back into liquid oceans, and for the chemistry to stabilize. but there would be no microbes left to restart the cycle of life. The evolutionary experiment would be ended, and the planet would remain a barren desert unless life were introduced from an external source. Thus, a giant kinetic impact is the ultimate terrestrial filter, an event that completely sanitizes the planetary engine by boiling its oceans and baking its crust. It is a demonstration of how kinetic energy can overwrite the laws of biology. But if a kinetic hammer of this size is a rare rarity in the modern solar system, there are other physical phenomena that can achieve similar results without ever touching our surface. There are entities in the dark that do not need to strike our planet to destroy its chemistry. They can pull the Earth out of its comfortable orbit, exposing it to the cold vacuum of interstellar space. To understand the next limit of survival, we must look at the rogue objects that wander through the galaxy and examine what happens when a gravity well sweeps through our system. When we analyze the physical limits of planetary destruction, we usually look at forces we can visualize. We picture asteroids gouging the crust or stellar radiation stripping the atmosphere. These events are governed by classical physics, where energy moves across space to collide with matter. But there is another category of threat, one that does not travel through space but instead rewrites the very fabric of space itself. This is the absolute quantum limit of physical reality. To understand it, we must change how we think about the vacuum. We think of a vacuum as a clean void containing nothing, a quiet stage for cosmic events. But in quantum field theory, the vacuum is not empty. It is a dynamic system filled with fields that dictate how particles interact. The most fundamental is the Higgs field. This invisible field permeates the cosmos, interacting with particles to give them mass. Without the Higgs field, quarks and electrons would have zero mass, flying at the speed of light without ever binding together. Atoms could not form, chemistry would be impossible, and life would never exist. The stability of everything we see depends entirely on the steady state of this underlying field. But here's what makes this truly mind-bending. The Higgs field might not be stable. Modern measurements of the Higgs boson mass suggest that our universe exists in a state of metastability, which physicists call a false vacuum. This means the vacuum we live in is not the lowest energy state. It is merely a temporary resting point, a cosmic shelf that could collapse under the right conditions. To visualize this false vacuum, imagine a ball sitting in a shallow dip on a high mountain ridge. The ball is stable for now, protected by the edges of the dip, but it is not in the lowest energy state. The true vacuum, the absolute lowest energy state, is the valley floor. If the ball is pushed over the edge, it rolls down, releasing massive kinetic energy. In our universe, the Higgs field is that ball on the ridge. It has occupied this metastable state for 13.8 billion years, giving us the illusion of permanence. But thermodynamics dictates that systems always seek the lowest energy state. The Higgs field is constantly under pressure to fall into the true vacuum. This is where the physics gets strange. In our everyday world, a ball on a ridge cannot move without a physical push. But quantum mechanics operates under different rules. Quantum tunneling allows particles to pass through energy barriers without climbing over them. Imagine a concrete dam holding back a deep reservoir. The reservoir represents the false vacuum, and the wall is the energy barrier. In the macro world, water remains trapped unless it rises over the dam. In the quantum realm, a microscopic droplet can tunnel straight through the concrete. Once that tiny leak is established, the pressure of the water will tear the dam, releasing the reservoir. In our universe, if a single point in space undergoes quantum tunneling, the Higgs field will drop into the true vacuum. This local collapse will release an enormous bubble of energy, initiating a chain reaction that cannot be stopped. But the real mystery lies in how this bubble behaves. This bubble of true vacuum is thermodynamically favored, meaning it is more stable than the false vacuum. Because of this, it will expand in all directions, its wall accelerating until it travels at the speed of light. As it sweeps through the cosmos, it carries the new state of the Higgs field with it. We would never see it coming. Since light travels at the same speed as the expanding wall, any physical signal of the bubble's approach would arrive at the exact same instant as the destruction itself. 1 millisecond, the night sky is normal, and the next, the solar system is gone. The speed of this transition means that the 2-hour horizon is rendered completely meaningless. The destruction occurs at the speed of light, giving no opportunity for response. This is not just a shift in states, it is a rewriting of existence itself. Inside this bubble of true vacuum, the physical laws of our reality are completely rewritten. The mass of fundamental particles changes, and the constants of nature are altered. In this new physics, quarks and electrons can no longer interact to form stable atoms. Carbon, nitrogen, and oxygen become physically impossible. The chemical bonds holding DNA dissolve, and water molecules lose their cohesive properties. The granite rocks of the crust, the oceans, and the atmosphere disintegrate in a fraction of a millisecond. They do not melt or burn. They are dismantled at the subatomic level, their constituent parts converted into new, alien forms of matter that are incompatible with chemistry. Yet the strangeness does not end with the speed of destruction. The bubble redrafts the vacuum itself, turning space into a silent, starless theater where the old forces of nature no longer exist. Against a vacuum decay event, there is no shielding. You cannot hide behind a mountain if the atoms in the mountain are rewritten. You cannot seek refuge in the deep crust if the space occupied by the crust is transitioning to a new physical state. The threat bypasses the structural defenses of the planet because it operates on space-time itself. The Earth is erased like a digital file deleted from a hard drive. It is an instantaneous sterilization that leaves nothing behind, not even a dead rock. The fundamental rules of nature do not care about geological shielding, since the shielding itself is made of the very fields undergoing collapse. But if the quantum field remains stable, the biosphere is not as vulnerable as it seems. We look at the surface of the Earth, with its forests and cities, and think this thin layer of life is all that exists. This is a surface bias. Beneath the soil, deep inside the granite of the Earth, lies a hidden engine of survival. It has run silently for billions of years, independent of the sunlit surface. To understand how life survives the worst disasters of our solar system, we must go down miles beneath the crust, where a secret ecosystem operates under its own laws, powered by the radioactive decay of the planet itself. The reason the Earth is so incredibly difficult to sterilize lies in the existence of the Deep Biosphere, a vast subterranean world that acts as the planet's ultimate biological backup system. For centuries, our understanding of life was confined to the surface. We assumed that the sun was the primary engine of all biology, and that without photosynthesis, the food chain would collapse. But deep crust drilling projects have shattered this assumption. Miles beneath our feet, inside the solid granite of continental plates and the basalt of the ocean floor, lies a complex network of microorganisms known as endoliths. Active communities of bacteria and archaea have been recovered from depths exceeding 3 miles down in continental crust and over 6 miles beneath the ocean surface. These microscopic organisms inhabit the tiny pores, fractures, and crystal boundaries of rocks, thriving in conditions that would instantly kill surface organisms. This subterranean world is completely decoupled from the atmosphere. To survive in these dark depths, life has evolved to exist without sunlight or atmospheric oxygen. Instead of relying on the surface energy loop, these deep organisms rely on chemosynthesis, drawing energy directly from the rocks. One primary pathway involves the simple reaction between water and iron-rich minerals. As groundwater slowly filters down through the crust, it reacts with iron oxide in the basalt, releasing free hydrogen molecules. The microbes, acting as chemolithoautotrophs, extract this hydrogen. They combine it with dissolved carbon dioxide to synthesize organic molecules, bypassing the need for solar light. But here's what makes this truly mind-bending. This chemical pathway is one of the oldest metabolic systems on Earth, representing a direct connection to the ancient biochemistry that first emerged on the young planet. It is a slow, steady chemical engine that operates independently of the surface world, drawing energy from the thermodynamic decay of the planet itself. This is where the physics gets strange. The deeper we go, the more we realize that water and iron are not the only things fueling this hidden biosphere. Deep within the continental crust, natural radioactive isotopes of uranium, thorium, and potassium are constantly decaying, emitting low levels of ionizing radiation. When this radiation collides with water molecules trapped inside rock pores, it splits them into hydrogen and oxygen. This process, known as radiolysis, is a constant, geological source of free energy. Subterranean microbes capture the hydrogen released by radiolysis, reacting it with sulfate or carbon dioxide to generate adenosine triphosphate. Through this mechanism, life is literally powered by the radioisotopes of the Earth, microbes living in tiny cavities of basaltic rock, miles below the surface, glow with metabolic life under the heat and energy generated by the slow decay of uranium. But the real mystery lies in how these organisms adapt to the extreme physics of their environment. Because nutrients are scarce and movement is restricted, the metabolic rates of these deep organisms are incredibly slow. Some of these microbes divide only once every century, living in a state of near-suspended animation. Yet, despite this slow pace, the sheer volume of the habitat is so immense that the total biomass of the deep biosphere is estimated to be equal to, or even greater than, the mass of all plant life on the surface combined. It is a massive, silent web of life that wraps around the entire planet, miles beneath the soil and the ocean floor. If an asteroid impact or a stellar flare were to sanitize the surface, this deep network would remain completely untouched, insulated by miles of solid rock. This is not just survival. It is a completely independent engine of biology, a quiet counterweight to the fragility of the surface. Subterranean life also features extremophiles with defense mechanisms that seem almost supernatural. The bacterium Deinococcus radiodurans, for example, can survive radiation doses thousands of times higher than what would kill a human. If its DNA is shattered into hundreds of fragments by ionizing radiation, it can reassemble its entire genome within hours, using specialized proteins to stitch the genetic code back together without errors. Other microbes can survive temperatures well above the boiling point of water, or thrive in hypersaline fluids deep inside ancient rock formations. These adaptations show that the boundary of biology is far wider than our surface-biased perspective suggests. Life is not a fragile film on the crust, but an active, geological force. Yet the scale of this hidden world challenges everything we know about the inevitability of extinction, revealing that the true heart of Earth's biology is buried deep where no cosmic storm can reach. This deep resilience highlights a profound contrast. The surface of our planet is vulnerable, a thin and fragile interface exposed to the vacuum of space, solar winds, and asteroid bombardments. It is a delicate leaf clinging to a branch in a storm. But the deep biosphere is the trunk of the tree. The base of life subterranean in the crust acts as the invisible engine of the Earth, immune to the shocks that periodically erase surface civilizations. It is the peak of chemical persistence, a beautiful demonstration of life's stubborn chemistry in the cosmos, completely decoupled from the sun. As long as the interior of the Earth remains hot, this underground sanctuary will endure. It exists in its own thermodynamic reality, a self-sustaining engine of survival. And this leads us to a stunning realization about the longevity of life. While the subterranean microbes can survive the impact of a massive asteroid or the stripping of the atmosphere, they cannot escape the long-term thermodynamic evolution of their parent star. We are living in a temporary window of geological stability. In the far future, a slow, unstoppable change in the sun will begin to alter the energy balance of the entire solar system. This stellar evolution will initiate a transition that not even the deep crust can buffer, starting a countdown that will eventually reach the deepest sanctuaries of the planet. As the solar furnace brightens, the outer layers of the Earth will face a quiet, unstoppable heating that will slowly push the boundaries of life deeper, until there is nowhere left to hide. The final chapter of Earth's biology will not be written on its surface, but in the deepest, hottest fractures of its rocky mantle, where the last survivors will make their final stand. The final threat to our planet doesn't come from a wandering black hole or a sudden quantum decay. It comes from the star we orbit. The sun is our source of warmth, yet it holds a quiet sentence of destruction for every living thing. To understand this, we must look inside the stellar engine, where hydrogen fuses into helium. This reaction keeps the sun stable, but it's not a permanent balance. As the furnace burns, helium ash accumulates in the core. Because helium is heavier than hydrogen, the core slowly contracts under its own gravity. But here's what makes this mind-bending. As the core shrinks, its internal pressure and temperature spike, which actually accelerates the fusion of the remaining hydrogen. The sun is forced to burn hotter just to keep from collapsing under its own weight. Every billion years, our star becomes 10% brighter. This 10% rise represents a massive surge of energy that will dismantle the delicate systems of Earth. Over astronomical timescales, this minor fluctuation becomes an existential hammer, driving the slow desiccation of our home planet. In about 1 billion years, this growing solar glare will spark a silent chemical crisis in the Earth's crust. As the temperature rises, it speeds up the chemical reactions between rainfall, carbon dioxide, and silicate rocks. This process, known as silicate weathering, acts as the natural thermostat of our world. Normally, when the planet gets too hot, weathering accelerates, extracting carbon dioxide from the air and locking it away in limestone. But this is where the physics gets strange. Under a brighter sun, this feedback loop runs completely out of control. The rate of silicate weathering will outpace the carbon dioxide released by volcanoes. The reaction will draw carbon down faster than it can be replaced, trapping it in a deep geological tomb. In a cruel twist of stellar feedback, the planetary thermostat will end up stripping the atmosphere of the carbon that keeps the biosphere alive. Within 800 million years, carbon dioxide levels will fall below the threshold required for complex plant life. When CO2 dissolves in rainwater, it forms carbonic acid, which eats away at silicate minerals. This carbon converts into bicarbonate ions, flowing into the oceans where marine organisms use it to construct shells, which eventually settle onto the seafloor as limestone. Under the intense glare of a brighter sun, this chemical cycle runs at double speed. But the real mystery lies in how the planet's decline actually unfolds. The Earth won't burn to death first. Instead, it will suffocate in sterile cleanliness. When carbon dioxide falls below 150 parts per million, the plants using standard C3 photosynthesis will wither and die. This includes almost all trees, agricultural crops, and wild forests. Within another 100 million years, even the hardier C4 grasses will collapse as carbon drops below 10 parts per million. The green surface of our world will degrade into a dry, brown desert, ending the production of atmospheric oxygen. Without plants to transpire moisture, the global water cycle will break and heat will build up on the bare ground. Today, the Earth has a cold trap in the lower atmosphere that keeps water from escaping into space. The cold air causes water vapor to condense and fall back as rain. But as the sun grows 10% brighter, this cold trap will fail. Water vapor will rise directly into the stratosphere, exposed to the unfiltered power of solar ultraviolet rays. This is where the planetary scale gets terrifying. Ultraviolet radiation will split the water molecules apart in a process called photodissociation. The heavy oxygen will react with surface rocks, but the light hydrogen atoms are too energetic for Earth's gravity to hold. They will stream into space, trailing behind the planet like the blue tail of a dying comet. Our oceans are literally leaking into the cosmos. By 2 billion years from now, the oceans will dry up completely, leaving empty salt canyons, and tectonic plates will lock up. But this is where the physics of resilience gets poetic. While the surface is a vulnerable skin easily scorched by stellar shifts, the deep subterranean life engine in the crust is immune to these stellar shocks. Without water to lubricate them, tectonic plates will lock together, freezing the crust in place. Without tectonic recycling, volcanoes will shut down, and the planet's magnetic dynamo will begin to decay as core convection slows. The solar wind will strip away the remaining atmosphere. Yet miles beneath this sterilized ground, a quiet biosphere will continue to run. Endolithic microbes, living in the deep fractures of basalt and granite, are completely unaffected by surface conditions. They don't need sunlight, oxygen, or rain. Instead, they feed on the chemical energy of mineral reactions and radioactive decay. This deep microbial motor is the true survivor of Earth, carrying on the flame of life long after the surface is gone, proving the sheer persistence of self-replicating chemistry in the dark. But even this deep shelter has a time limit. Without oceans to radiate heat, the thermal energy of the sun will conduct directly into the solid rock, baking the crust from the top down. Slowly, the temperature miles beneath the seabed will rise past 120 degrees Celsius, the absolute limit for cellular life. The proteins and genetic codes of the last microbes will dissolve. This slow, relentless sterilization is a thermodynamic certainty, written into the evolution of our star. The Earth will be left as a dry, silent monument of basalt and granite, orbiting a sun that continues to swell into a red giant. This dying star will eventually engulf the inner planets, leaving the outer reaches of the solar system as the only potential havens. But this leaves us with an open loop. If simple life is resilient enough to survive in the deep crust of a dying world, could similar microbial communities be surviving right now in the dark corners of our solar system? The answer to that question shifts our focus from the death of Earth to the wider galaxy. If the story of Earth teaches us anything, it's that basic life is almost impossible to destroy. We've seen how microbes can survive miles beneath the surface, feeding on rocks and radioactive decay. They don't care about solar flares, ice ages, or asteroid impacts. Because of this resilience, simple single-celled life must be incredibly common in the universe. It doesn't need a perfect biosphere. Microbes are likely clinging to the warm rocks deep under the frozen crust of Mars, where liquid aquifers still run. They're probably drifting in the warm, salty oceans underneath the ice of Europa and Enceladus. But here's what makes this mind-bending. Europa alone holds an ocean with twice the volume of all Earth's oceans combined, sealed under a shell of ice 15 miles thick. There are trillions of rocky planets in the Milky Way, and many of them have the geological heat and water needed to support this deep, hidden biology. If the universe is a machine for creating life, then the cosmic basement is crowded. But if basic life is everywhere, we face a haunting question: why is the galaxy so quiet? This is the Fermi paradox. We've pointed our most powerful radio telescopes at thousands of stars, searching for signals, and we've found nothing but static. The silence is deafening. It suggests that there's a barrier, a massive obstacle that stops simple microbes from evolving into spacefaring civilizations. Scientists call this the Great Filter. The transition from a rock-eating microbe to an intelligent technological species is not a smooth, guaranteed path. This is where the physics gets strange. The evolution of complex cells, multicellular cooperation, central nervous systems, and eventually abstract thought are not inevitable outcomes of biology. Each represents a narrow bottleneck, a filter where millions of species might stall forever. The filter might lie behind us, meaning the step from single cells to complex cells is almost impossible. Or it might lie ahead of us, as a wall that has destroyed every other civilization before they could reach the stars. To understand this barrier, we must look at the difference between survival in the deep crust and survival on the surface. Microbes underground are protected by miles of solid granite, keeping them immune to stellar shocks. But consciousness requires a surface. To build a technological civilization, a species must emerge from the dark. It needs access to solar energy, fire, and metals. It must build cities, factories, and space centers. But the real mystery lies in how this transition shifts the balance of risk. The moment a species steps onto the surface, it leaves its geological shield behind. Suddenly, it's exposed to the cosmic void. We don't have 2 kilometers of solid rock to protect us. Instead, we rely on a thin, delicate skin of gas, our atmosphere. If you compared the Earth to an apple, our atmosphere is thinner than the skin. We are entirely dependent on this fragile shield, and it's vulnerable to a dozen cosmic anomalies that could strip it away in days. Our fragility is not just biological, it's also technological. We've built a global network of communication, power grids, and computers. This technosphere is our strength, but it's also a massive liability. It's vulnerable to the whims of space weather. Our cities and power grids are connected by a delicate web of copper and fiber optics, vulnerable to a single high-energy pulse from our star. This is where the planetary scale gets terrifying. A solar storm like the Carrington event of 1859, which melted telegraph wires, would collapse our modern electronic infrastructure if it hit us today. It would plunge our cities into darkness, stop the flow of water and food, and destroy the global economy. On top of that, we have to deal with our own internal instabilities. We've developed the power to split the atom and rewrite genetic code. But we haven't lost our tribal instincts. We're a young, volatile species that has built weapons of mass destruction before learning how to live in peace. Despite this fragility, the human mind has achieved something extraordinary. We're the first species on this planet capable of mapping the universe. We can calculate the orbit of distant asteroids, measure the temperature of newborn stars, and predict the death of our own sun. We're the mechanism through which the Earth has become conscious of itself. But here's the twist that most people miss. The mind is the bridge through which the universe understands itself. If we disappear, the flame of observation on this world goes out. The universe will continue to expand and stars will continue to burn, but there will be no one to witness the show. Raw physical data will drift through empty space, unread and uninterpreted. We're the bridge between the physics of the cosmos and the realization of its meaning. We stand on the edge of the horizon of consciousness, representing the Earth's best hope of escaping the limits of a single planet. We're the consciousness of Earth facing the filter, standing at the very edge of our own fragility. Our existence is a brief, glowing spark in the cosmic dark. The timeline of our star is ticking, and the window of opportunity is narrow. We must find a way to secure our intelligence before the physical changes of our planet and the instabilities of our technology pull us back into the silence. We have the tools to understand our situation, but we must have the collective wisdom to survive it. If you want to understand how a civilization can escape this delicate surface before the star claims it, click on this video here, where we explore the physics of interstellar colonization and the escape velocity of the mind.